All right, welcome. In this explainer, we're going to break down the one fundamental equation that makes every single transformer work. Let's get right into it.
You've definitely seen these everywhere. They step voltage up or down, but the real magic behind how they do it? Well, it all comes down to a single, really elegant piece of physics. So let's peel back the layers and see what's actually going on inside. So here's our game plan. We're going to build the transformer equation from the ground up, step by step. We'll start with one single law of physics, see how it plays with AC power, and then assemble all the pieces until we get to that simple, powerful ratio that makes it all tick.
Okay, let's dive in. Our foundation, our absolute starting point, is Faraday's law of induction. This is where the whole story begins.
This equation right here, this is the key. Now, I know it might look a little complex, but the idea is actually incredibly simple. You can create a voltage, what physicists call an electromotive force, or EMF, but, and this is the important part, only if a magnetic field is changing over time. A static magnet just sitting there, it won't do a thing. It's all about that rate of change, that little d/dt part of the equation. That's what makes all the difference.
Now let's make this a little more real. That total magnetic field passing through our coil, we call that the magnetic flux, and we use the Greek letter phi for it. And here's the cool part. By wrapping wire into a coil with a bunch of turns, we'll call it N1, we basically multiply the effect. Every single loop of wire contributes, adding to the total voltage we get out.
So we need a changing magnetic field. And where do we get one of those? Well, we get it from an alternating current, or AC power source. You know, the stuff that comes out of your wall outlet. Its constantly changing nature is literally the engine that drives this entire process.
And because our AC power supply alternates so smoothly, the magnetic flux it creates inside the transformer's core does the exact same thing. It produces this beautiful, continuous sine wave, building up to a maximum, dropping down to a minimum, and just repeating that cycle over and over.
So what happens when we take that sine wave for the flux and plug it back into Faraday's law? Well, remember, that law is all about the rate of change. And a little bit of calculus tells us something really neat. The rate of change of a sine wave is a cosine wave. You don't have to be a math whiz here. Just remember that result, because it's absolutely crucial for what's coming next.
And this diagram shows that result perfectly. See, a cosine wave is really just a sine wave that's been shifted over by 90 degrees. What that means is the voltage that gets created, E1, is always lagging behind the magnetic flux that created it in the first place. They are constantly out of sync, and that 90-degree phase shift is a fundamental property of how all transformers work. Pretty cool, right?
Okay, so now we're ready to start putting these pieces together. We're going to build the practical equation that we can use for real-world calculations, moving from pure physics theory to something an engineer can actually get their hands on and use.
To make our equation useful, we can't really work with the peak voltage because, it's always changing. So instead, engineers use what's called an effective value. It's called RMS, which stands for root mean square. Just think of it as the steady DC voltage that would give you the same amount of power. It's just a really handy way to find a useful average.
And for a sine wave, the conversion is just wonderfully simple. All you have to do is take the maximum voltage, the very peak of that wave, and divide it by the square root of 2. Boom. That gives you the practical RMS value that you'd actually see if you put a multimeter on it.
Now, this whole process, taking Faraday's law, bringing in the sine wave, and converting to RMS, it leads us to this one kind of weird-looking number that shows up in the final equation, 4.44.
So where on earth does 4.44 come from? It's not magic, I promise. It's just a convenient little package of all the math we just did. It's got constants like pi from the sine wave, it's got the square root of 2 from our RMS conversion, and it even has another property called a form factor. Basically, 4.44 just bundles all that theory into one simple number for our final equation.
And here it is, the final practical EMF equation for our primary or input coil. It tells us the RMS voltage, E1, is just 4.44 times the frequency, F, times the number of turns, N1, times the maximum magnetic flux, phi m. All the pieces are finally in place.
Now here's the best part. That same magnetic flux that the first coil created, it's also passing right through the second, or output coil. So the exact same physics applies. We can use the very same equation for the voltage on the secondary side, E2, just by swapping in its number of turns, N2. It's that simple.
So let's put our two equations together. When we do this, you're about to see all the complex parts just fall away, and what's left is the beautifully simple principle that is the absolute heart of every transformer.
Just look at this. If we set this up as a ratio, dividing the secondary voltage equation by the primary one, watch what happens. The 4.44 cancels out. The frequency? Gone. The magnetic flux? That cancels out too. Since they're the same for both coils, they just disappear.
And here's what we're left with. All of that physics, all of that mass, boils down to this one incredibly simple and elegant relationship. The ratio of the output voltage to the input voltage is exactly the same as the ratio of the number of turns of wire on the coils. That's it. You want to double the voltage, you just double the number of turns. It is literally that direct.
Now, it's important to note that elegant equation describes a perfect, or what we call an ideal transformer. So before we wrap up, let's just take a quick look at what makes real-world transformers a little more complicated.
So in our ideal model on the left, every bit of magnetic flux is perfectly contained and links up with both coils. But in the real world, on the right, some of that magnetic field actually leaks out into the air and doesn't make it to the second coil. On top of that, the copper wire itself isn't a perfect conductor. It has some resistance. These little real-world problems, shown as R and X here, mean that a real transformer is always going to lose a tiny bit of energy.
So to recap the journey we just took, we started with Faraday's law, right? A changing field creates voltage. We saw how AC power gives us that change as a nice sine wave. We totally demystified that magic number 4.44, and it all led us to the most important part, the core principle, that the voltage ratio is simply the turns ratio.
You know, we've talked all about voltage, but that's really only half the story. Which leaves us with a final question to chew on. If you step up the voltage, what do you think has to happen to the current to make sure we don't just create energy out of thin air? That's a great story for another time.